right, Ben, do you want to start? Or should we wait
I
for?
think we wait for a couple more.
Hello, everyone. Welcome to today's Quantum Matter Journal Club. Today we are having Ben Eller to give us a talk on natural transition orbitals. Ben is a graduate student with Professor Charles Clark on AMO theory. So yeah, Ben, take over.
Hello. So today we'll just be talking about this brief communication from back in 2003, written by Richard L. Martin. He was at Los Alamos, describing what are termed natural transition orbitals. So here's the abstract for this this brief little paper. The basic idea is that we'll be looking at trying to look at electronic excited states and make a little, make some sense of them, because say sometimes the way that electronic excited states are described is non-intuitive, if that makes any sense. It's, maybe it's like mathematically correct, but it doesn't help us, it doesn't provide, a nice understanding of what's going on. And so that's one of the things Martin was trying to address. And the takeaway message that I'd like, hope everybody to remember is that orbital descriptions, we like orbital descriptions of electronic behavior because it helps us develop an intuition about what's going on. The prototypical example being, the behavior of an electron in a hydrogen atom. There it's at, it's exact. You have an exact description of the electron's behavior in terms of the wave functions for the eigenfunctions for the hydrogen atom. But when you get to, multi-electron atoms, or worse, molecular systems, solid state systems, more complex, many atom systems with many, many electrons, you would like to retain such a description that you use in, like, say, the hydrogen atom or a single particle situation, but it becomes more difficult and, it's less clear what's going on. Because electronic, transitions, they often involve, so there are approaches to understanding many electron systems in terms of orbitals, but then when you try to describe the excited states, they involve oftentimes many transitions between these single particle orbitals you're using to describe the ground state. And so it doesn't really tell you much.
I think even for ground state, like sometimes it's impossible to have an atomic insulator description. For example, if you have a Chern number, then it is impossible to have a local one orbital decomposition.
Well, so would you, so could you give me an example of such a system?
So for example, you have Chern number, such system is non-trivial.
Could you give me a specific example of a system? I'm not being a what?
Do you know what is a Hauldin?
No.
So you have a honeycomb lattice.
Okay.
With the second nearest neighbor, with the nearest neighbor hopping without a phase, and the second nearest neighbor hopping with a phase. Okay. The second nearest neighbor hopping breaks time versus symmetry.
Okay.
And creates Chern number, 1 or -1, depending on your direction. Like the experimentalists call this quantum novelist Hall effect, because there's no extrinsic magnetic field that breaks the time versus symmetry. So such.
Well, are you saying that, so like, I guess graphene would be an example of such a system?
Yes.
Okay.
You can actually realize this, for example, twisted butterfly.
Well, so I guess, are you saying that, for instance, you can't do a Hartree-Fock calculation? I mean, you can, I guess you could, but it's not going to.
You cannot decompose into orbitals on different sites. You cannot decompose your wave function.
Yeah, well, okay, so I would say that in orbital description doesn't necessarily have to refer to like a Wannier function, kind of like a localized orbital description. In fact, so for like a metal, the kinds of orbitals you might see would be incredibly delocalized over the entire structure. But you still, so the orbitals they come from like, from my understanding, like the prototypical example is like doing like a Hartree-Fock calculation on a system. And there you get, your ground state many electron wave function is a Slater determinant that is constructed from a set of single particle orbitals, which are the eigenfunctions, I believe, like the solutions of the Hartree-Fock equations. Now, how good that, how good of a description that is of the ground state, varies on the system, right?
If you don't have interaction, you can always exact diagonalize your system.
Yeah. Well, it all depends on the interactions, right? Like Hartree-Fock throws stuff away, right? I believe like correlation doesn't address correlation of electrons at all.
I mean, without interaction, you can calculate correlation.
Well, correlation is a type of interaction, is it not? In terms of like electron-electron interaction?
Well, it depends. I guess I'm talking about correlation function.
I'm talking about correlation energy. Sorry.
So,
The energy, the interaction energy associated with the correlation of the motion of different electrons, I believe. With that, it kind of depends on the theory. Like a DFT, a density functional theory approach, technically, it kind of can vary based on how you approximate this exchange correlation energy.
So DFT can solve problems with interaction.
Yeah, it's in principle, DFT gives you exact solution, but only for the ground state, but only if you actually knew the exact exchange. It kind of creates this effective potential, but you don't actually know what it is. So you have to make approximations, and that's where it becomes an approximate solution. You basically just roll all of the.
You just have an exact solution.
Yes. Well,
but it has an approximate solution for the excited state.
Well, so the density functional theory itself refers to ground state, the ground state of a mini electronic system. If you look at the excited state, that's when you start to talk about a time-dependent density functional theory. Even if it doesn't actually, you might not even be dealing with time dependence, but you might be looking in frequency space, but giving you optical excitations. But density functional theory is it refers to a ground state solution, self-consistent field solution. So we'll say in some sense, I think you always do have, you can always approximately solve something. How good of an approximation or not kind of depends on your circumstance. But in doing so, many of the methods involve some sort of single particle description where you have a set of eigenfunctions. They're single particle orbitals, and you start filling up these orbitals with electrons, obeying the Pauli exclusion principle, or obeying, you need an antisymmetric wave function. So excited states of electronic systems, you can think, starting from this, you have a ground state configuration, you have a bunch of orbitals, and you've started occupying these orbitals with electrons. And since they're spin orbitals, really, and each spin orbital can either have no electrons or one electron, due to the Pauli exclusion principle. Okay, so then you could imagine you've got your ground state. Now you can imagine you also have a bunch of eigenfunctions from the same procedure that are not occupied in the ground state. They're in the virtual space, so-called. So if we look here, we can look at this, the so-called Kohn-Sham equation. Just for a specific example, let's imagine performing a density functional theory calculation to obtain the ground state of an electronic system. So we do that by solving the Kohn-Sham equation, which is seen here. If you look at it, it's an eigenvalue equation. You get a bunch of eigenfunctions and they have associated eigenvalues. And then what you do to get the ground state density is you start filling up these eigenfunctions until you run out of electrons. And then the electronic density is given by the sum of all these single particle densities. If you're, if you had, so the approximate nature of this procedure comes in the VXC term. This is the exchange correlation potential, which is by definition, all of the interaction effects that are not included in the classical Hartree energy, which this U of N here, which is just your typical classical electrostatic potential. So depending on your approximation for the VXC, that's going to, tell you how approximately correct your ground state is. So once you run out of those, you also have a bunch of these eigenfunction, these psi s that, they're not occupied, but you have them from the calculation. And so, let's see. Right, so you have a set of your occupied set of single particle or spin orbitals that are all filled up in the ground state. And then your virtual unoccupied orbitals, which are labeled with the prime. And they're just sitting there unoccupied in the ground state. And so what we're going to do, you can think of some excited state as being some, really what you do is you look at this transition density matrix, and the element, the matrix element is given here, where you look at, if you look at it, what you're doing is psi 0 is your ground state configuration. So you're removing a particle from the occupied space and you're adding it to the virtual space. Now, just to note, in this paper, I finally realized that the C and C dagger here are actually creation and annihilation operators for holes, which is just the reverse. So you destroy a hole in the unoccupied space and create a hole in the occupied space of the ground state. So you basically, we're just talking about single excitations from the ground state. And your actual excited state it's not any one of these. It kind of, depends on the excited state. It can be some combination of these.
Good question now here. So usually when we're talking about the excited state or excited electron, we talk about behaviors near the Fermi surface.
Yeah.
So does this transition density matrix necessarily require the electrons near the Fermi surface or not?
That's a good question. I would say from practical experience, it's all, at least it kind of, I guess it would depend on your particular excited state you're looking at. So for me, I'm looking at like, not ionization or anything. I'm just looking at low line optical excitations. And it's going to, in that case, it always involves, orbitals from near the Fermi surface. Usually like, you'll have like HOMO to LUMO transitions, but maybe like, I'm sorry, are you familiar with the HOMO-LUMO acronym? Sorry, in chemist land, HOMO is highest occupied molecular orbital. LUMO is lowest unoccupied molecular orbital. So that's referring to this. See, here you have psi I. So psi in occupied, that's your highest occupied molecular orbital. And then psi prime 1 in this designation would be like your lowest unoccupied. And you're right, for these kinds of just low line optical excitations, and in fact, a lot of behavior just involves transitions around the Fermi surface. But I could imagine maybe a different kind of excited state that would, you know what I mean? Maybe like a really heavy, maybe not an ionization procedure, but like a near ionization threshold photon coming into a system. I don't know for sure, but it might involve many more, I would imagine.
What if you don't even have a Fermi surface? You have a non-Fermi liquid. Can this theory describe something?
I have no idea. I'm not
Have a
sure.
Very high interaction.
Strongly interacting. That's a good question.
And then you don't have the firm surface.
I think in this
That's interesting.
in this DFT method, they kind of starts from the Hartree-Fock
Mhm.
approximation, and they and all the higher order interactions like loop corrections, they are containing the pseudo potential.
So there are perturbations to the.
Yes,
Hartree-Fock
like in
approximation.
their formalism, yes. However, I kind of doubt that like there are probably like in the very highly interacting systems, like all these methods may fail,
Yeah.
especially, yeah, because they are based on the fundamental like Feynman diagram calculations.
Yeah,
from the theory side.
it all stems from like everything interesting that we like kind of say quantum mechanically interesting to us, like all the work now is this last term here. It's the exchange correlate. It's because it's by definition in the of the DFT, it's by definition everything that you've neglected by writing your potential like this. And so based on, we don't know what it is in general, because it can be for any arbitrary system. And so you're exactly right. If you don't, for instance, if you use the simplest and most maybe you could say most popular and straightforward approximation to the exchange correlation is so-called local density approximation, where so we know for a homogeneous electron gas, we know the exchange correlation potential. So what they do is they say, well, the exchange correlation energy is like that of a homogeneous electron gas with the density evaluated at that point. That does not all, of course, that just fail. It works surprisingly well in some cases, but then it's going to fail in others. And so
if there are
you're
like
right.
lower
If you have,
order, like during which the exchange interactions are not described by local densities, then I think this method will not work. Right.
You'd have to have some better VXC. And they use a lot of times now, it's very popular to use so-called semi-empirical functionals, which in some sense you might be unsatisfactory because it's like, let's use lots of experimental data, some models, but also some experimental data and do fitting to to a large data set. And then, we'll say it gives you good enough energies within this data set. So, and there's your functional.
Okay. Yeah. I think we can proceed.
Yeah. Okay. Right. So that's the basic picture. We're looking at excited states, and we have some set of spin orbitals from your ground state procedure for specificity, something like a DFT calculation. Now you're describing your excited states in terms of where'd it go? A bunch of these, you have a matrix connecting a bunch of these occupied and unoccupied single particle orbitals, but it's like, great. How does this help? How does this help us understand what's going on better? And that's where this idea of the natural transition orbitals comes in. And we're looking at this transition density matrix T here. So this is difficult to interpret in an intuitive manner. So here's a nice specific example of that from Martin's 2003 paper. For example, he looks at this rhenium atom complex. So with if you look at, so here where it says description, this is the not natural, just the description in terms of your single particle orbitals from your ground state calculation, just the regular description that we've been talking about. And if you notice, both excited states 2 and 3 here, they both involve, apart from a phase, a phase factor, you see the negative sign, they're described as like this highest occupied, HOMO minus J. Is that clear how you have the highest occupied molecular orbital, then you have HOMO minus 1 is the next lowest energy occupied molecular orbital, and so forth down. And then LUMO, lowest unoccupied molecular orbital, and higher. Is the designation clear?
Okay, yes.
Okay.
You can proceed.
And okay, so you see how these states are described in terms of like a HOMO minus 2 to LUMO transition with a HOMO minus 1 to LUMO transition. both of them, in fact,
Yeah.
apart from some phase factors. But
So factors, like parameters that you fit into the, I think lambda max is the overlap to the.
so these factors here in this description, they so we're looking at this here, this transition density matrix. Imagine this excited state bra here being a linear combination of a bunch of these singly excited configurations. So it's some psi excited, some overall state, and it's composed of a number of these transitions between occupied and unoccupied orbitals.
So what's the difference between natural orbitals and
We're getting to that. So so the psi, yeah, I should have written this out actually. Psi excited is like a linear combination of these singly excited electron configurations of the system. Let's see if I can, for instance, one example of a singly excited configuration. You have all of these psi, they're all filled in the ground state. Now you take the one from the highest occupied molecular orbital, the psi N0, and you excite that to one of the virtual unoccupied orbitals here. That's a singly excited configuration, okay? You've taken the electron out of an occupied orbital and you put it in an unoccupied orbital.
Yeah.
And any particular excited state is some linear combination, it's not, you can't just, it's not described always. Sometimes it is, but it's not described as a direct transition from one orbital to the other. Does that make sense? You've done this, calculation. You've got a bunch of these orbitals that construct your ground state. But an excited state is not necessarily a direct excitation from,
Yeah, maybe it's easier to understand with an example.
I think I probably should try to come up with a good visualization of it, maybe.
I think you can.
Right. So sorry for the people on the recording, but here, I think if we look at the blackboard real quick, I can just, here's your ground state. Each of these, you put electrons in these single particle orbitals. And then your ground state wave function is a Slater determinant.
Yes.
Formed from these orbitals, okay? For example, an example of a singly excited configuration. You take one of these electrons, you also have all these unoccupied orbitals up here. Now you promote one of these electrons to one of the unoccupied orbitals, okay? But your psi excited might actually be A times this plus B times another, a different excitation. Was that clear?
For example,
Like, instead of exciting this orbital to that one, you could excite this orbital to this one. And now your actual excited state is a linear combination of all of these.
And
that's where these numbers come from.
Yeah. So
That's where those numbers come from.
won't they
They're
contribute to the
do
same?
you fit this to a numerical result?
No, this is a result of a excited state calculation. You have, it's just an input. You're given this. It's some excited state and it's a linear combination of these singly
So
excitated.
it's even possible to encode a selection rule.
Yes, absolutely.
By saying that,
Yes.
for example, A is 0 to eliminate some of the.
Yes, absolutely. Right. For sure.
So if for example, if we have configuration like this, won't the configuration in A and B cost the same energy or no?
Possibly not.
Possibly not.
Right. And again, the actual excitation is some combination of them. And this is part of where that's kind of confusing, right? Like it's kind of hard to understand what's going on when you have, let's say you had 30 of these different configurations, singly excited configurations,
Yes.
contributing to your overall excited transition.
Yeah.
That would be like, I don't really understand what's going on here.
Then what's the
That's
difference?
what we're trying to get at here. We're going to do basically a mathematical procedure on this matrix.
Yes.
It's basically just a change of basis
Okay.
and tried the idea. I think it's basically a change of basis to a more natural basis, and we'll see
Okay.
why natural. Why the natural?
Sigma summation is just the.
So spin configurations, right? So oftentimes if you can either do spin unrestricted or spin restricted, I forget spins. So that, and again, that's where these numbers here, this is like a linear the excited state is a linear combination of these single promotions.
Yeah.
And those numbers are giving you not, in fact, they're complex coefficients, right? It's a general linear combination. That's why both of these excited states actually involve the same two promotion, single excitations.
Yeah.
But, they're actually qualitatively different if you look at the oscillator strength, so the light measure the likelihood to emit a photon by decaying. Right, lambda max we'll get to, right? That's from the natural transition orbitals. So this description here is your regular description. And so the problem for me here is we're saying we're exciting an electron. There's an excited electron and it got excited from two different holes. HOMO -2 and HOMO -1 orbitals are both a hole, or the hole is a linear combination of the two. It's a kind of a little weird. We would like to, our brains would like to operate in terms of what got excited to where, as Martin puts it.
Okay.
It's nice to know what got excited to where, and this doesn't really tell you that.
Yeah.
Right. Yeah, this is not very satisfactory. And so that lambda max, actually, this is a eigenvalue from your what we're about to talk about. What do we do about it? What do we do about this? And what did Martin do about this in 2003? And in fact, as he mentions, he's performing a procedure that has been used in different contexts multiple times in mathematical language. It's a singular value decomposition. If you're interested in the math, you can look up singular value decomposition. And that's in essence what is being used here. So what Martin does is defines two new sets of orbitals. You have your psi's and your psi primes from your ground state density functional theory calculation. And you also have you've obtained an excited state by a time-dependent density functional theory calculation. And as we discussed, it can be expressed as some combination of these single excitations. Now, Martin defines two new sets of orbitals, the phi and the phi prime, in the following manner. So this is basically, it's applying a singular value decomposition to both the T dagger and the T dagger T.
What is T?
T is your transition density matrix.
Oh, okay.
That's the matrix elements being this TIA right here. Let's see. Now, if you notice, let's see. Right, so the T dagger actually brings you to the occupied space. T is not a square matrix.
Yeah.
It's like kind of depends on your occupied and your virtual space. It's going to be some in occupied times in virtual rectangular array.
Yeah.
But then if you look at T dagger and T dagger T, these are respectively just square in occupied by in occupied and in virtual by in virtual matrices. And then we define these new matrices U and V, which are obtained with these eigenvectors, the UI and the VI. And so the U and the UI and the VI are just column vectors.
Yeah.
So these, the U and V are really made. It's kind of, the notation he uses is a little, you kind of have to dig through it. But yeah, the U and V are matrices. And then these phi and phi prime here are vectors. Even though, I think, okay, it's clear. Okay, good. It took me a while to actually be like, wait, what's going on? Okay. So, it's like, okay, great. Now, if you notice, there's these lambda I and lambda I prime, and the I's run, either from the up to the number of occupied orbitals or up to the number of virtual orbitals. Now, the thing about the phi's is, in the phi primes, is they have these following properties. And this is where the natural, I think, comes into play and why they're useful. So if I'm quoting here, it breaks it down real nice. The lambda I and the lambda I prime. So again, that's coming from these, we're decomposing the occupied and virtual orbital spaces separately. And so we have these separate eigenvalues, lambda I and lambda I prime here. If you number them in order of decreasing magnitude, then it's true that they're bounded, they have an upper bound of 1. And lambda I is equivalent to lambda I prime for a given I. So is this clear? It's kind of, so you'll have these sets of the lambda I, much of eigenvalues, from decomposing your occupied space. And then you have another set of lambda I prime you get as eigenvalues from decomposing your virtual space.
Yes.
And then if you just separately write them down, you start numbering them 1, 2, 3, and you do that in order of decreasing magnitude. So that lambda 1 is equivalent to lambda 1 prime. Lambda 2 is equivalent to lambda 2 prime. Is that clear?
Yeah.
And this is so they come in pairs. They come in pairs in decreasing magnitude with an upper bound of 1 and also a lower bound of 0. So they're positive semi-definite. I corrected on that earlier. Not positive definite, positive semi-definite. They can be 0, but they're not greater than 1. And they come in pairs for the occupied and virtual space.
This numbers, right? What do you mean equivalent?
They're exactly the same.
Equal.
No, like literally equivalent, not even by definition, but like if you go through the procedure and you number these lambdas in order of decrease, it's it's kind of, there's an element of arbitrariness here. You don't have to order them in terms of decreasing magnitude, but you can. And when you do, then you have this property, which this is what, so when you're, well, actually, I won't get into that. There's within a certain, the so-called Tamm-Dankoff approximation of time-dependent density functional theory, or equivalently, configuration interaction singles approach. Then the sum of all these lambda I, they add up to 1. And if you
Wouldn't that be, can we interpret that as the matrix norm of all the transition matrices equal to 1, like that's for the probability 1 interpretation?
I think so, yeah, it's very suggestive.
I think if you just normalize your t, you can just get 1.
Well, so
for example, you times 1 over determinant t.
Yeah,
so-
A square root determinant.
Yeah.
it's 1 within a certain approximation. If you don't do that, there's also and this actually shows up in my research, is these things they call de-excitation operators. Still trying to figure out what they are, what they refer to. They are ignored in the Tamm-Dankoff approximation. If they're included, this sum won't actually be 1, but it's usually close, which is.
So you're saying that all the possible excitations in real physical systems may not add up to 1 according to the DFT approximation.
No, so actually, let's not talk about. I don't know too much about it. I'm still trying to learn it's only. I'll just say this. This only adds up to 1 within a certain approximation of time-dependent density functional theory.
Okay.
That does a very good job.
Okay.
So
yeah.
just forget about what I said about de-excitation operators.
Yeah. Now
entirely.
I think I sort of understand what it means.
I
So,
think you're right. You can interpret, it gives you an interpretation. This adds up to 1, right?
Yeah.
You know,
Sean, I think the essence here is the sum all up to NO.
yes.
So I think there are cases when you can, we know that if we sum over all the possible bases, like from 1 to n, like n representing all possible states, that definitely equals to 1. But here he's truncating it into NO.
Mhm.
Why are we computing?
Well,
Uh,
first of
that's
all,
because
this
of the
this isn't like a completion relation or anything.
Yeah,
This
yeah.
isn't saying a sum over, it's not a sum over
Yeah.
outer products or anything. This actually is, again, this is mathematical, like singular value decomposition. He's kind of just quoting mathematical properties of singular value decompositions, which in some sense I think is kind of like diagonalizing non-square matrices. If you can think, you basically just factor any m by n matrix into a factor of 2 unitary matrices and a diagonal matrix. So in some sense, it's a way of diagonalizing non-square matrices.
I think we can proceed.
Okay, right. And so that's summing up to 1. These lambdas were really square root of lambda, I believe. Or no, lambda. Square root of lambda are the singular values. The lambda are called occupation numbers because of this summing up to 1 thing. I think is kind of that's where I felt like they came up with the term. You know, you have a transition, right?
Yeah.
You have a bunch of these particle hole amplitudes, and then if you include all of them, their total contribution, they, you know what I mean? Like all of these particle hole amplitudes contribute to that excited state.
Yeah. But what I'm saying is that NO here in practice, it may not be like an infinite number because we like in practice you can only represent it with a finite number of transitions.
Certainly, right.
Even so here, suppose NO is 10. Suppose there are only 10 excitations, which we already did a lot of approximations. Although this does not satisfy the complete relation, it still works approximately. I think that's what Ben means in the DFT.
I mean, we're physicists. As long as
Yeah, we're used to these things. Okay, we can proceed.
Right, and so basically speaking, the larger this lambda, for a given particle. So what you see here, that this lambda I equivalent to lambda I prime. This is how you say, okay, I have an orbital phi, see phi prime that corresponds to your lambda prime.
Yeah.
And you have an orbital phi that corresponds to your lambda.
Yeah.
And this is how you can connect the two because they're lambda, there's like 2 lambdas that are exactly the same.
Yeah.
And that's how you can say, so these 2 orbitals are kind of connected. One of them is in the occupied space. So we interpret that as the whole, right? Where, in the occupied orbital space. And then there's now an orbital in the virtual space that is the excited particle. And they have this, the greater the lambda is, the more important that particular particle hole amplitude is for the overall excited state.
So A is just particle hole. Is that?
What?
That's not.
Huh?
There's no particle hole symmetry.
No.
It just give you like an association of like the canonical hole of a particular.
A labels virtual, A labels particles, I labels holes, basically. They're just labels for to distinguish.
And I are the same.
Yeah, the I and A are just labels.
But are the numbers the same?
They can be.
But when you say when you align them in decreasing or increasing order,
right.
And they're equivalent, you're implicitly assuming that they have the same number.
Yes, when you do that, right, exactly. When you do that, they do have the same.
But this is not necessary.
Well, see, so
O(n) and V can be different, right? The number of the lambda.
NV is greater than or equal to NO.
We still have some zero eigenvalues.
Yes, right.
So
Right.
So
A number of them are just 0.
So is this because we're picking a particular basis, or we calculate them to be 0?
No, they
I mean, it's surprising that they're exactly zero.
it is. And I wish I was a better mathematician and I could talk about the
But they are exactly.
I have a text. We should talk about this. Yes, they're exactly, exactly zero. There's a number of them. And I'll tell you, it goes up. It's for all the ones with where they're labeled, it's up to the rank of A, up to the rank of your matrix. If you have an n by, a non-square matrix, it has some rank R.
Yeah.
It's all the eigenvalues for the greater than rank that are zero. Yeah. Yeah, it is just linear algebra. You're absolutely correct. It is just linear algebra.
Yeah, we can proceed. Yeah.
Right. So, and this is why, this gives you this nice, okay, now we have a bunch of these orbitals, pairs of orbitals where, one of them's in your, as a whole space and one of them's in your excited space. And they have these, eigenvalues, these singular values of decreasing magnitude, telling you how important each particle hole is to that overall transition.
Yes.
Now, and the transition density matrix expressed in terms of these new orbitals is, that's what we're doing. We're diagonalizing the transition density matrix, basically.
Yeah.
That, and then their entries are given by the square root of your occupation numbers.
Yes.
That's, so before we had a description of some excited state in terms of in occupied times in virtual different orbitals in principle. In practice, it might have actually been simple in practice. Sometimes I find I have excited states that are simply homo-lumo in terms of just the original orbitals are just homo-lumo transitions. And you're like, well, there's only one thing. That's what this excited state is, right? That's fair. But what if you have 5 or 10 of these different transitions? Then it's kind of, in principle, I guess you could have N0 times NV, separate important transitions contributing to an excited state. And I don't even know what to do with that. Now we just have N0 particle hole amplitudes. Because again, all the lambda, the lambda N0 plus 1 and greater are all 0.
Yeah.
Right. And then the magnitude of these singular values are telling you how important this is. But now let's see. Martin goes through a quick use a practical implementation of this idea based on this. So, I'm not going to attempt to give you the name, but there's some atomic metallic metal ligand complex with a rhenium atom in the center of it that we're looking at. Now you see what the lambda max is, right? So lambda max here in this table, that's the maximum, after doing this this natural transition orbital procedure, that's the maximum singular value you get.
Okay.
Which is to say, see how close that is to 1. That means that those transitions they're not exactly 1, so there's some other particle hole amplitudes involved, but they're very close to 1, which means those states, can be thought of in terms of one single dominant, there's a hole, we excited the system and it left this hole and it created this excited particle. And that's your state. And of course, I think this is like T equals 0. What happens to it after that? This doesn't tell you. And that's actually where that dynamical transition orbitals comes into play. But maybe for a later day. So, now we can actually, let's look at, he plots, here are these NTOs pairs for these 3 excited states of this, rhenium, was it CO3? I don't know, ETPY, I don't know what that is. This thing here. So now if we, the excited states are labeled 1, 2, 3, and the whole orbitals are on the left and the particles are on the right. So now you can see how, and he notes in the communication, look at the holes. They're all kind of around the central metallic atom, the rhenium atom.
I think we have about 9 minutes left.
Yeah, all right. This is wrapping up actually.
Okay.
And so So you're here, it's clear you have you've excited for each of these, you've kind of excited a hole around the ring, the interpretation of this is, which I think we should be clear. We're interpreting this as a whole, a particle being excited from the rhenium atom and moving out to one of the ligands out on the side.
Just want to be clear, this is supposed to be a metal.
Yeah, it's some kind of metallic ligand complex. So there's a rhenium if you see, I think it's kind of hard because it's blue and it blends into the background, but right there. So you have your rhenium atom right there. And then you've got a lot of it looks like hydrocarbon, like stuff around it. So that's kind of not, rather than looking at this description here, right, where we're like, I don't know. I mean, I guess you'd have to plot these orbitals, but oftentimes they're kind of, they're not nice and intuitive like this, where, man, we're transferring a particle from that metallic center out to the sides. And you can even see how, interesting. Yeah, the particles all look very similar, don't they? But the whole amplitudes all look kind of different, I would say, just qualitatively speaking. Interesting. Anyways, so yeah, this is, I don't know, this is back in 2003. I'm not really sure what he used. He's got using Gaussian 98 as this.
I don't know.
Does he say? It doesn't seem to say what they're using for the plotting. Yeah, I'm not really sure. It doesn't look from, I can't even give a guess as to what they're using. It doesn't look the output doesn't look familiar to me. Well, interestingly enough, though, so I've actually, just as a, coming to a conclusion here, I've tried to, apply this to research, right? So you can actually go into, so Gaussian, the suite of programs, has this, you can implement this with a keyword in Gaussian. If you have an excited state, to say you've run use Gaussian, you did some kind of time-dependent density functional theory calculation, you got an excited state, and then you want to run this procedure, you can do it. So I did, it's just, for example, looking at some nanotube segments with some defects, just because.
What kind of defect is
it? I don't have it.
Do you have a?
It's a covalent, two hydrogen atoms, covalently bound and close to the carbon nanotube surface. Around so here I can. Yes, again, sorry for the people online. You get to miss out, but if you look at just the local graphene, kind of lattice structure of the nanotube. Yeah, we just need one. Here we go. That's terrible, but whatever. So basically, here's your carbon atoms. The defect here is you have a little hydrogen atom here, and then bound to the carbons there on the surface.
So this is a local defect.
Yes,
This is not a dislocation.
Correct.
It's
a local chemical defect. Correct. In fact, we would refer to these in the business as an SP3 defect. Often there's a bunch. There are new kind of.
Did you study lattice defect?
What do you mean by lattice defect?
Do you know what is a dislocation?
Yeah, somewhat. Can you
Dislocation.
I'm thinking of a picture of a lattice, and you take part of it and you kind of shift it away from the rest of it, or
Yeah, basically.
okay.
Yeah, do you study?
No, I don't even. That sounds actually kind of difficult. I don't know. Or it seems a lot different than these kinds. I mostly deal with these kinds of defects right here.
Well, okay. Could you write down Hamiltonian for this? Is it possible, or it's just?
We'll talk more about that later. That's an interesting question. I don't. Maybe. I mean, technically, yes. I can. I can write down the Hamiltonian.
Fine.
I can write down any Hamiltonian of any system, atomically defined system. Can I solve it or do anything with it? No, not necessarily. Are you referring to like an effective kind of Hamiltonian description?
Right.
That's something that we'd like to develop, actually. It's an interesting question. You can definitely do this Hamiltonian for this. You can define this. Yeah. This is what Gaussian does. It solves these equations for this.
It just
That H psi equals E psi. That's your Hamiltonian. That's your Kohn-Sham Hamiltonian.
well.
Yeah, right. So technically,
that is an approximation.
well, it's only an approximation. Again, it's only an approximation insofar as you approximate this term here. Technically speaking, although not practically speaking, but technically speaking, it's an exact reformulation of the ground state many-body problem. But you don't know what this is. And so you have to approximate this. And so just like anything you do in many-body physics, it's always an approximation. Almost always. There's very few exactly solvable situations. Or at least I should say the number of exactly solvable models divided by the number of not exactly solvable models is 0. So yeah, I have this system, and I did ground state calculations with DFT, did time-dependent density functional theory, got some low-lying excited state information. Here's in terms of the original, I don't know what to call them, the original orbitals, self-consistent field orbitals from the DFT. Here's one of this excited state transition that corresponds to, God damn it, this emission feature right here, the B3. So there it is. There's the orbital description. It makes even less sense than the example here, right? Like, I mean, it's got this is what I'm talking about. It has even more of these occupied divergential transitions to where I'm like, I don't know what to do with it. And so you look at the natural transition orbitals. Okay, now I wish this is my mistake. I should have labeled, and maybe in a different talk, I have the singular values for these. These are your particle, whole particle, your natural transition orbital pairs plotted. And so so this H0, E0, that's got some lambda associated with it, and so forth. And I've, they're of decreasing importance. I labeled them in terms of decreasing lambda, right? Is that clear? What I mean? Like in terms of this, I've labeled these particle whole pairs and I've plotted them in terms of decreasing magnitude. So this top one here is the most dominant, and then these start to contribute less and less. And then there's other ones. So actually what I found with this specific, and I don't really understand this yet, this specific system, the natural transition orbitals that seem to do really well here in this particular system, this rhenium complex, this procedure doesn't seem to provide me too much, or at least it's not obvious that this simplifies things.
What is your lambda max?
That's a good question. I think it's like 0.8, something like 0.8. So it's still, I think it does help a little, but it's not as like, there isn't just bam, one, it would have been really nice. I was hoping that I would have used this procedure and be like, wow, there's that excited state. Look at that. It's just like he does, with this rhenium complex, like, man, this excited state moves electron from there to there. It's not as, I think it might be more natural for some systems than other systems, if that makes sense.
Is it because your system size is too large? It seems to be much larger than it is.
Oh, it's a very large system. Yes. I don't know. I don't know why.
The system size and see,
I mean,
maybe a finite,
that's a good,
scale.
that's an interesting question. Like I should try it on, there's a molecule that these are armchair nanotubes, which means they have an armchair edge that kind of like that on the.
Does these zigzag and armchair have any significant difference?
Zigzag and armchair?
Yeah.
Vastly so, yeah. Armchairs are all metallic, whereas zigzag nanotubes can be metallic or metallic, or which means they're actually really small gap semiconductors, but at room temperature, they're basically metals or semiconducting. And then there's the achiral nanotubes that are, I think they're all semiconducting. So it could be finite. There's like a molecule that can be seen as like the basic building block of armchairs. I should apply it to that.
If you have a very large nanotube,
Yeah.
it's effectively a 2D system. There's no
2D.
reason-
I'd call it 1D.
Well, I mean, a very large nanotube.
Yeah, large diameter.
Yeah, large diameter.
Large diameter nanotube is graphene.
Right. So
Yeah.
there must be some phase transition.
Right.
Like, when you decrease the system size,
Yeah.
it's split into two different phases. Because in the graphene case, I don't see there's a distinction between phase and arm.
You're right. I mean, so the distinguish, the distinction arises, now we're kind of, I guess this is kind of, we're kind of done with thank you for your attention. We're done with the natural transition orbitals portion of it now. I think we're just kind of freewheeling at this point.
Yeah.
So like, should I stop the recording?
Yeah.
I think we're done. Thank you for your attention.
Thank you.
And then we can keep discussing